I extend to you our warmest island greetings of Hafa Day to all of you on behalf of Chelu, our organization in San Diego, our Chamorro diasporic community of California, and our Sacman Chamorro crew. And thank you, Dr. Simon, for bringing the primer up so that we're on page 1. I am the son of a carpenter and a fisherman. And today I come with purpose to share with you what we have learned about the Marianas flying proa, to share with you the mathematics that we have discovered when building our single outrigger canoe, and to share with you our excitement when we discovered that form follows function. I want to introduce the few members who are present here on our Sacman Chamorro crew. We have Pete Perez. He is part of our research, and I tell you what, he's done a lot of work to get us to where we are. We have Greg Perez, our senior canoe builder. He's right there. And special thanks to Uncle Frank and Auntie Meming Shimizu for coming out from Guam to be present in today's presentation. Saina Maasi. Thank you, Frank. Thank you, It indeed takes a team to build a canoe, to sell her, and to maintain her. And thank you for your support. I must preface that building a canoe does not make you a sailor. It does not. It helps, but it does not. Here's the canoe we built, a 47-foot single outrigger canoe made from a single California redwood from the National Sequoia Forest here in Mendocino, California. It weighs 5,600 pounds dry and floats in 18 inches of water. This picture was taken at Shelter Island in San Diego back in 2011, the very year we completed her construction. We call our canoe the Sacman. Yeah. How we got here is the story we tell often. But today we focus on the highlights of our efforts that now we can call our empirical mathematical experience. And to appreciate this mathematical experience, we must look at what has brought us here today. In fact, it was another canoe that has brought us the inspiration to build this canoe. There she is, the Hokulea. The Hawaiian double-hulled canoe came in on the 22nd of July, 1995 into San Diego Bay. Her presence, was majestic. She was such a beauty. Indeed, she captured the hearts and admiration of the many Pacific Islanders who came out to greet her. For us, the Chamorro people, it ignited our curiosity. That her presence that morning inspired us to research our own seafaring histories and to question if there was any connection of such large vessels like this to our small islands in the Marianas. You see, growing up in Guam, we learned more about the Nina, the Pinta, and the Santa Maria. Our canoes were not in the curriculum. If we look at the many small islands in our Marianas archipelago, all 15 of them, ranging from Guam at the southernmost to Uracas at the north, 420 nautical miles separation, you would suspect that there was such a connection that there must have been large canoes that transported people and cargo from island to island, and your suspicion would be correct. Our curiosity led us to this drawing that we found in the British archives. And thank you, Senor Pete Perez, for doing all that research. It is entitled The Anson Drawing of 1742. This is a classical engineering drawing, I must say, of a 40-foot Sacman, one of the largest sailing vessels our Chamorro ancestors built. It shows 3 views, the front view, the side view, and the top view. Along with these views is the scaling data. It was from this very drawing that we constructed our flying proa. We started with models so we can understand the math involved, the tooling that we need, and the craftsmanship demanded of us. More importantly, we build models so we can gain the confidence to go go the last mile and build the full-scale canoe. When we started building these models and finally our 47-foot proa in March of 2010, everything that we did, everything that we stumbled upon was a discovery. 21 years later, that very ancient drawing led us to this event, where the Sackman was at its speediest to date. And we have a lot of time left. We hit 17 knots on Guam in June of 2016. At 10 knots, the hull started to hydroplane. At 15, the outrigger started to lift. And at 17, she started to fly. Yeah. I'll tell you what, we were on full adrenaline at that time. Let's get started. Let's look at the parts of the proa. Now, Dr. Penny also brought up several parts of the canoe, but I'm going to focus on the proa itself. This layout is similar to the sailing canoes in Micronesia. We have the hull, the main body, the outrigger for balance, the booms that connect the outrigger to the main hull. The mast is a single mast, non-fixed. It holds up the sail. The sail is our Latin-shaped triangular sail. It's our basic propulsion system. The steering paddle, not shown here, is for direction control. And you don't see the 6 crew members, but it does take 6 crew members to handle this beast and to do all the above work. All our mathematical discoveries can be found on this one drawing, and it involves these parts you see here. There are 11 discoveries that I want to share with you today. From the basic string mathematics, our ancestral system, the scaling mathematics, simple in relationship, but it's really challenging in just keeping record of. The length of the keel is a function of the log. Not logarithm, the log, the wood. How's the math? It's going to be difficult here. The length of the booms is a function of the length of the keel. And the outrigger placement is a function of the keel and the boom together. The length of the proa is a function of the keel. The length of the diagonals, a function of the length of the proa. The mast length as well is a function of the length of the keel. The length of the outrigger is a function of the wood density. The hull design is a function of purpose. And the closest angle to the wind is a function of the diagonals. Now, these 2 previous slides show that many of the measurements on the proa are functions of the keel length. Now, this makes sense because when you start building a canoe, you start out with a log, what turns out to be your keel. This is the beauty of the flying proa. Math discovery number 1. String mathematics. The string. And this has a purpose. I'll tell you a story. When I went to Maui to help build canoes with Chief Bruno Tarngan of Yap, I brought along with me a DeWalt 25-footer measuring tape. He looked at that, he laughed at me, and told me to toss it out. I did. And he had around his neck a string, just like this. A string that equated in length to the measure of his keel. And with that string, he showed me how to add. If you want to add this to that, you got it. If you want to subtract this from this, you pinch it. And if you want to divide something, you fold it. If you want to multiply something, well, 1, 2, 3. If you have a 100-foot string, you can go to 100-foot multiplication. And dimension equality, if you want to measure the diameter, you fold that string around the girth of the log. Parallel, it's easy to do. By definition, parallel lines are equidistant, right? Well, you can use this for your distant measurement. If something is perpendicular, you want to check for true situation of perpendicularity, like the stays, for example, make sure that the stays are equal. If the stays are equal, guess what? Perpendicular by definition. And like Chief Bruno always tells me, if all fails, you use your eyeball. Eyeball, he would always tell me. Math discovery number 2, scaling. This is the math tool that we use when we want to build a larger or smaller version of the flying proa. The real discovery is finding out the actual dimensions and of the parts of the flying proa built in 1742, the Anson proa. The Anson proa is about 40 feet long, 28 inches wide at the center, 43 inches high at the beam at the center, and 75 inches high at the bow. Now, if you didn't have a measuring tape, you would know that. But, because these things are not marked off in inches. The Anson the Anson mass itself stands about 23.5 feet. If we wanted to build a 47-foot like we did, 47-foot canoe like we did, we would divide the two numbers and get a scale factor of 1.175. That's 47 divided by 40, and we use that throughout our calculation. The new mass for the 47-foot canoe would turn out to be about 27.6 feet. Discovery number 3. Given the selected log to serve as the keel, the length of the keel is fixed. Unless you got a variable trunk. But you don't. A string equal to the length of that keel is cut and kept by the master carver, and Chief Bruno had the string around his neck. It would serve as the main reference for other parts of the canoe. Hence, the length of the string equals the length of the keel, and here is how we measure the keel. From this cut all the way to the other end, that will be the keel. This little diagram shows that the canoe is actually built in parts. You have the keel, the bow, and then the sides. And everything is tied together by rope. Discovery number 4. From observation, now that we know the length of the keel, we can easily find the length of each of the 3 booms that hold the outrigger. 1/2 the length of the keel equates to the length of the boom. Now, use string theory and you measure it off, you can confirm that. The boom length is also equal to the distance between the outer booms. So once you've got the keel, you've got the length of the boom, and you've got the measurement that separates those booms. Number 5, from the wisdom of our ancestors. This relationship that we learned in Maui in 2008 came from Chief Bruno again. Chief Bruno of Yap. And this is what he showed me. He asked me to go out, and you know what? I didn't speak much Korean, neither did he. He asked me, he gave me this tip. And with sign language, I understood what he wanted me to do with this. He told me, he pointed at the keel. I went around until he said, okay. That means okay. I left it there, and he pulled this end all the way to the end of the boom. Then he tells me to take that piece, and of course, sign language again. I went to the gunnel where the boom, the center boom, met with the hull of the canoe. And when he pulled that thing back, he pinched off where the boom length would be. And guess what he did? He went like that. That was the difference, right? Mm-hmm. A minus B, or in this one, K minus B. I used K for the keel and B for the boom. Guess what he did? He folded it. Division by 2. So I came up with, I said, wait a minute. This is a math opportunity. learning opportunity. So I read down and I wrote down in my notebook. I said, oh, K minus B divided by 2 equals X. And then I said, what's X? Huh? Then he took that and he asked me to make pieces of wood, 2 pieces of wood. Turned out to be spacers. Spacers that he would put in between the outrigger and the boom. And that became the separator. Now, for the answer drawing, this is that separator. This is what I put. Can you imagine I'm holding it now? A 1742 canoe. I have that X. It's a wonderful feeling. And math is so fun. Oh, there's so much fun in mathematics. Number 6. The ratio of a proa's keel length to its overall length is pretty much constant for most of our canoes. So, the length of the keel divided by the length of the proa is about 0.7, plus or minus 0.03 perhaps. But let's say it's 0.7. If you have that, then the length of the proa is actually 1.4 times the length of the keel. So you have that dimension. This defines proportionality and stability in form and function. Now, when I was in Guam, I met with Tony Pialuk. Tony, there's Tony back there. And he was working on a canoe. And I asked him, how long would that canoe end up to be? And he goes, he looked at it, pondered, seemingly to do some calculations. Then he said, 18 feet. Well, guess what? That length of that keel was. It's 12.5 feet. If you do that math, it comes out to be 0.69 ratio. That's pretty close for string theory. So, it's common in the work that Tony was doing, in the work that we're doing, and in the answer drawing as well. Number 7, from observation again, the length of the diagonals that I highlighted there in dotted line, the length of the diagonals is equal to the length of it's a function of the length of the proa. In this case, it's half the length. Now, these diagonals extend out from the main hull to the outrigger to provide rigidity to the entire vessel, connecting the body of the main hull to the outrigger structure. It is basically a triangular truss system. So, the discovery is the length of the diagonals is half the length of the proa. Discovery number 8. Even the length of the mast is determined by the keel length. Now let's look at that triangle in the bottom right. You know, if you took the Pythagoras theorem, it tells you that that hypotenuse D is equal to the square root of the sum of the squares of the smaller sides. And if you do the math, it comes out that the length of the diagonal there is about 23.49 feet. And earlier I said the mast using string theory was 23.5. Pretty close for string theory. Number 9, determining the optimum length of the outrigger. It's a bit more involved. I mentioned that it's a function of density. Now the purpose of the outrigger is to provide balance, not only in static conditions, but in light and fair conditions, but also in windy conditions. Now, if you put your hand up like this is where the boom is, and this is where the outrigger sits. Guess what this represents? The sail. The only thing fixed is the distance out to the outrigger and the weight of the outrigger. And the weight of the outrigger is determined by the density of the wood that you use. Now, density is weight per unit volume. That means that the longer it is, the heavier it would be, the shorter it would be, the less. The cross-sectional area, length and cross-section area is equal to volume. So you can vary the amount of weight that you select for your canoe. The mast holding up the sail, on the sail, the only thing variable on the sail, it's a fixed area, but the wind upon it is the only variable. So you have to determine how much of a lift that you need. So that becomes a little bit more complex. As a general rule, the length of the outrigger is greater than 1/2 the length of the keel, but less than 1/2 the length of the proa, just for handling purposes. Number 10, symmetry and asymmetry. I know Simon mentioned this, but let me be complete here. The symmetry is obvious when you go in the side view or the top view. You see that the left side looks like the right side and the right looks like the left side. That is by design so that the canoe, because the canoe can actually go in either direction. The asymmetry. If you look at the front view or even the top view, you see that one side is flat and the other side is bellied up. The flat side acts like a keel to minimize your leeward slip. Aha! Now we come to something a little bit more fun. Points of sail. Before I share mathematical discovery number 11, I want to set the stage here with the basic points of sail. These are the classical points of sail identifying the direction of sail with respect to true wind. Now, if we look at the no-sail zone, Simon mentioned that it is impossible to sail directly into the wind, but you can really come close. Theta in that no-loan zone is somewhere between 45 and 60 degrees for Simon's kind of canoe boat. The proa can sail at all of these points of sail as long as the windward side, but the canoe is on the windward side, and he mentioned that as well. But the question is, how close can the flying proa sail into the wind? What is theta min? That's always been a question with sailors, and call it the Holy Grail. But guess what? We've got the answer for the flying proa.
Wow.
Yeah, it's 36 degrees. Here's how we find. How we came across that. We were out in the water. We knew where the wind was, right out the bay. I knew it was to my right, so we went on beam reaching. All right? That means just 90 degrees with respect to the wind. Then I asked my helmsman to turn into the wind. And he obeyed, and we turned into the wind. We pulled the sail closer and closer. And I asked him to direct this diagonal that's fixed, a fixed component on the canoe, directly into the wind. And he did. And that sail was put in tighter. And I'll tell you what, we gained more speed. And then we turned into the wind further. We lost speed. We went back to the direction that the diagonal was pointing at, right into the wind, and we regained speed. That's the closest sail angle that the flying proa, this flying proa, our flying proa, a 47-foot canoe, can muster. Wow! That item below our feet, below the helmsman, is indeed the indicator to shoot into the wind. There's no guessing. It's built in. And you know what? This brings the subject of wisdom from our ancestors. I'm sure they trialed and error this and that but yet they built it into the canoe. And sometimes we go on an artifact search, we look for things buried, for secrets. But our ancestors built the secret right into the canoe. And we're so blessed, and with our canoe builders now, the kids that are apprenticing, they're going to find this thing out and they're going to experience and appreciate the wisdom of our ancestors. Now, the math we have shared with you today is based on empirical data. From our time studying the ants and drawing, the time building the several models, to the time that our 47-foot Sackman was in the water sailing into the wind. Mathematics is indeed embedded in the very design and the structure of the Marianas Flying Proa. Sir George Anson, that was mentioned earlier, had a similar perspective some 275 years ago. He knew that the Marianas Flying Proa was a marvel of Chamorro simplicity and ingenuity. He even wrote one sentence in his book, Voyage Around the World, that eloquently summarizes it all. He wrote in his book, one sentence, "These Indians are no ways defective in understanding, for their flying proa in particular, in ages past, have been the only vessels used by them, are so singular and extraordinary an invention that it would do honor to any nation, however dexterous and acute. For if we consider the aptitude of this flying proa to the navigation of these islands, which all of them lay upon the same meridian, and with the limits of the trade wind, it would require that these vessels made use of in passing from one island to the other, to be particularly fitted for sailing with the wind upon the beam. Or if we examine the uncommon simplicity and the extraordinary velocity with which it moves," he said, "we shall, in each of these articles, find that it worthy of our admiration and deserving a place amongst the mechanical productions of the most civilized nations where arts and sciences have most eminently flourished." He wrote this in 1742. And you know what? That summarizes how simplistic our designs were and how ingenious our creations were. I hope that what we have just uncovered, the empirical data, the mathematics, and the Marianas Flying Proa, I hope that it has pushed the envelope just a little bit, albeit one canoe at a time, in our ocean of knowledge. I appreciate your presence.
Would you